Okay, strong versus weak when we talk about acids and bases have very specific meanings. And it's different than what you probably have used in the past. Uh, Normally, a lot of people think of strong acids as that if you have a very low pH or the acids that are very concentrated are often called strong, and those two concepts are different. We'll get more into that tomorrow. But our definition for strong here, okay, is something a strong acid or base will dissociate. Okay, it will dissociate completely. Okay, in water solution. Now, what do we mean by completely? 100%. All the way. Okay, all of it. It completely dissociates. So do not discount this word. This is the operative word in the definition. Okay, don't say, well, it dissociates. No, it dissociates completely. This is the important word for a strong acid or base, as compared to a weak acid or base. Okay, a weak acid will partially dissociate in a water solution. Okay, so not 100%. Okay, incompletely. The opposite of the strong and weak are supposed to be opposites to each other. The opposite in the definitions is complete versus incomplete, not dissociate versus not dissociate. Are we clear on this? Okay. So a weak acid or a weak base will only some of the molecules that are in solution will actually dissociate into their ions. Okay, which brings us to what dissociation actually is. What is dissociation anyway? Dissociation is the separation. It is the separation of an ionic compound into its cation and anion. Okay, it's separating the ions is the dissociation. This generally happens in water, but it doesn't have to. All right, so does water dissociate? Okay, yes, it does, and you've actually seen the water dissociation, or you've worked out the water dissociation in the last problem of the PDawg from yesterday. Okay, so what you will have is you'll have two water molecules, and they will create the hydronium ion and the hydroxide ion. And I want you to know those names. That this is the hydronium ion, and this is the hydroxide ion. This is the acid, this is the base. And hopefully from this equation, you can see something interesting going on here. That for every one of these that gets made, you make one of those. Well, if this is the ion that determines the presence of an acid, and this is the ion that determines the presence of a base, and for every one of these that you make one of those, you'll never have more of one than the other if you just have water. This property, by definition, makes water neutral. That it is neither acid or base because it has both parts in equal amounts. Okay? We'll dive more into this tomorrow, but this is an important concept. Okay? Now, if we were to add to this, actually let me finish drawing here. If we were to add to our water a substance that would make more of the hydronium ion than the hydroxide ion, then you have an acid, and that substance that you put into the water is considered an acid. And if you have a substance that you put in there that creates more hydroxide than anything else, or than the hydronium, then you have a base. Okay, so this is what water does to dissociate. Okay, so we're going to start with a strong acid. So what do acids and bases do? Strong acid. Okay, the example we're going to use is hydrochloric acid. Okay, so hydrogen chloride by itself, it can be crystallized. And if you were to create hydrochloric acid, you can create a crystalline HCl, which is pretty nasty stuff if you were to actually touch it, because the moisture in the air and the moisture in your hand would make a really concentrated HCl. And so you don't want to touch this stuff. Okay, but when you do put it into water, it will dissociate completely, because it's strong, into hydronium and chloride ion. And by the way, we are using these colors according to the CPK. No, not California Pizza Kitchen. No, Shubin. Okay.
I was actually going to say that.
Because you've been in my class all year. Okay, CPK are the initials of the chemists that came up with the idea of how to better show molecular drawings and molecular models and keep them consistent without like putting letters on them and labeling them. So if you looked at it, you would know exactly what kind of atom goes where, and it makes it easier to identify what molecule you have, because you can see where the carbons are, you can see where the nitrogens are. It was primarily done for organic chemistry, but it works well for us here. Okay, so this next statement we're going to write down is the practical application to this. What's that? This is a positive yes. Thank you. All right, and it's this statement. Okay, that a 2.0 molar hydrogen chloride solution will produce a 2.0 molar hydronium ion concentration. That every single one of these, every mole, every fraction of a mole of the HCl that you put into water will separate into HCl and make hydronium ion. And it doesn't go back. That's why this arrow is only one direction. So then we have strong bases. Okay. The reason I have the H2O put in parentheses is that it needs to be there in order to dissociate the sodium and the hydroxide. Sodium hydroxide is a strong base. It needs to be there to dissociate, but it's not actually, we're not taking one of the protons away from the water to create the hydroxide. The sodium hydroxide brings it with. And because it completely dissociates, so here's the sodium hydroxide, and it separates into its sodium, which is it's got its positive charge, and the hydroxide is a negative charge, and this is it. And here's our, and so we can make the same statement that we wrote down here, that 2 moles or a 2 molar solution of sodium hydroxide will produce 2 moles of hydroxide. That a 2 molar solution of sodium hydroxide will lead to a 2 molar solution of hydroxide. It'll also lead to a 2 molar solution of sodium ion, but this doesn't have anything to do with it. This has no effect on the acid or base properties. However, an interesting thing here. When we are describing something as having the properties of a base, we call it alkali. Okay, you may have heard of this word before. Okay, alkali metals, our far right column over there are alkali metals. Those are called alkali metals because when they are put in water, they make bases. Put sodium in water, it's going to make sodium hydroxide. Okay, you put lithium in water, it's going to make lithium hydroxide. You put magnesium in water, it's going to make magnesium hydroxide. They all make these bases when you put the alkaline and the alkali earth metals into water. So, something that is alkali or alkaline, okay, means basic. Okay, so when I say what is its alkalinity, okay, or how alkali is it, you're telling me what is its base properties? What properties does it have that are like a base? How bitter is it? Slippery, that sort of thing. Okay, that's for strong bases. Now, notice that both of these, strong bases and strong acids, have single arrow, one direction. They are not reversible. Now we have weaks. The weak acid we're going to use is hydrogen fluoride. There are other weak acids. The demonstration we're using is hydrogen fluoride. It will still dissociate, and it will dissociate into the predictable way. HF will donate a proton to water to create hydronium ion, and it'll be left behind by its conjugate base, the fluoride ion. And F by itself. Okay, however, what happens to any kind of reaction that is reversible? It will achieve equilibrium. Whenever you have an equilibrium, okay, there is a place for its solution where you have your balance of forward versus reverse reactions, right? When we have that balance, we can create our equilibrium constant. Okay, and so there is an equilibrium constant for an acid. It is called the Ka, which is the acid dissociation constant. And you write it, and the expression is just like you were creating an equilibrium expression. The Ka equals the concentration of our products divided by the concentration of the reactant. However, water is considered a liquid. It is considered pure. Because of that, it is an exception, and you don't include it in your expression. And this is our acid dissociation constant. This would equal some number, and this number is particular to hydrogen fluoride. When you see this Ka, if you're told that there's a Ka, if it has this value to it, then that means that this is a weak acid because it has this equilibrium of dissociation and non-dissociation. Our last one is our weak base, and it's NH3, and it dissociates into, okay, if this is a base, it's a Bronsted-Lowry base. This was the case that we used to show that the Arrhenius definition for an acid isn't good enough. We need to come up with a better one. And because this is a base, this will accept a proton, and it will take a proton away from the water. And it will make for us then NH4 positive and leave behind the hydroxide ion that we need to show that we have a base. All right, so what do those look like? So now we got this ion floating around. Is this what we're going to be looking for when we find our base? The NH4 positive, the ammonium ion? No. This is what gives us our base. The hydroxide concentration tells us how concentrated our base is. Not how strong it is, how concentrated it is. This is an equilibrium, and because of this, we will have the base dissociation constant. And it's created the same way. Kb equals our ammonium concentration times our hydroxide concentration all over our ammonia concentration. Okay, and these will give us the equilibrium constant. Now, just as a concept, if the Ka is large or the Kb is large, that means we're creating a lot of acid or we're creating a lot of base, right? Because the numbers on top are going to be larger than the numbers on the bottom. So the larger the Ka, the larger Kb, the more it's going to dissociate when it's at equilibrium. The smaller the Ka, the smaller the Kb, the less it's going to dissociate. Yeah? Okay. That's really it. Okay. Your homework assignment tonight, which is due Thursday for you guys, is to complete the strong versus weak acid POGL. Okay, complete that whole packet. We will have another assignment tomorrow. It's going to come out of your book, but the strong versus weak acid POGL is the primary. Okay, is your primary assignment right now. So that's it, and